In my previous video, I stated De Morve's theorem, which is raising a complex number to a power. And we can use that in our advantage to create for ourselves a number of trigonometric identities. So if we take the general complex number of modulus 1, so cos of theta plus I times sine of theta, and I can raise that to the power n. And what I'm going to do is use De Morve's theorem on this. So that is identical to cos of n theta plus I times sine of n theta by De Morve's. And I can also expand this using the binomial expansion. And then once I've got the binomial expansion, I can equate the real parts and the imaginary parts to what's over here, and that will give me a trigonometric identity for multiple angles of either cos or sine. That's the general process. So let's have a look at an example of this, a particular example. So let's raise this to the power 3. So we're going to cube it. So this is obviously going to be equal to cos of 3 theta plus I times sine of 3 theta by De Morve's theorem. But using the binomial expansion, I can say that this is cos cubed plus 3 cos squared sine I am writing shorthand, minus 3 cos sine squared. Okay, the I squared has become minus 1 here. And I'm going to get minus s cubed I, where the I cubed has become minus I. So I can equate the real parts and the imaginary parts of this to give me two identities. So the real part is cos of 3 theta is identical to cos cubed minus 3 cos sine squared. So I get that cos of 3 theta is identical to cos cubed of theta minus 3 cos theta times sine squared of theta, because that's the real parts of this using De Morve's and this using the binomial expansion. I then could, of course, replace the sine squared with 1 minus cos squared by that well-used identity. And then I can multiply out the brackets and simplify. Cos cubed plus 3 cos cubed is 4 cos cubed. And minus 3 cos times 1 leaves me with minus 3 cos theta. So therefore, cos of 3 theta is identical to 4 cos cubed of theta minus 3 cos of theta. Of course, I could do exactly the same, but equate the imaginary parts. So in this case, the imaginary part is sine of 3 theta, 3 cos squared sine, and minus sine cubed. And that will give me sine of 3 theta, the imaginary part, is identical to 3 cos squared of theta sine of theta. Don't need the I. Okay, the imaginary part is the coefficient of I. I don't need to write the I in. Sine cubed of theta. And again, I can replace this cos squared with 1 minus sine squared. Sine of theta minus sine cubed. And then I can combine the like terms. So I get 3 sine of theta. And I'll get minus 3 sine cubed minus a fourth. So it's minus 4 sine cubed of theta. Okay. So therefore, sine of 3 theta is 3 sine theta minus 4 sine cubed of theta. Very similar to this one, except there's a sign change. Have a go for yourself. Let's look at the 4 thetas. Have a go at finding A, B, C, and D in these identities. Notice that for sine of 4 theta, you will need to have a coefficient of cos out there. Otherwise, you'll have a funny square root kicking around, which is never fun. So we write it as cos theta into a function of multiple powers of sine theta.